set my counter here. So, good afternoon. I'm Dean Tribble, Brian Warner, and we're here from Agoric, and very grateful to Cosmos folks for having us and for giving us this vehicle. We've been here since the beginning of the week working on IBC, and you'll see some of where that fits in here. We are a company founded by people who've been working on smart contracts for, oh, my thing didn't respond to my button here. Hang on. Oh well. I've been working on smart contracts for, all right, there we go. I've been working on smart contracts since before there were blockchain. So to us, a smart contract is a contract-like arrangement expressed in code that where the operation of the contract is enforced by the execution of the code. So it's doing rights transfer, the execution of the code does that. Now obviously before blockchain, we had to do that with cryptographic protocols between machines where you find a mutually shared party to run your code on, but it would really truly enforce the rights transfer that you were engaging in the contract. With blockchain, we end up with, so that would give us what we call solo machines. Server machines, laptops, phones, what have you, where they're executing code that is doing some kind of rights transfer. What blockchains brought us is new computers built out of agreement rather than silicon, but the same kinds of models, the same kinds of ideas operate on that, and that's why smart contracts are running on blockchains, and because they can run on blockchains with so much higher integrity, it's got a resurgence of interest and a lot more use cases that are valuable across the economy. So our model of cryptographic protocols between machines means we have a model that can run within a blockchain, within a permission chain, a quorum network like a Hyperledger or something like that, or on individual machines. And then above that, so Agoric is building an entire stack all the way up to a rich contract library. I'm going to work my way up very quickly in the description of those layers, and then we'll focus on some of the technical implementation details. So above the, our model of computation is these units called VATs that are islands of sequential programming inside of a sea of asynchronous messaging between these islands. We'll talk more about that, but those red lines there loosely correspond to IBC, and that's a lot of why we just started collaborating with ICF and All in Bits on the implementation of IBC, because that hits the right chord and is the technology stack that we were already working on, and now we're building something that will solve both of our challenges there. Above that, we have a programming layer designed for object capabilities. We'll talk more about that. And that's the layer at which we write programs that operate in a distributed fashion within chain, between chains, across machines, and so forth. And finally, above that, we have the electronic contract. Oh, and then messages flow around. And finally, above that, we have the framework for building smart contracts. So at this level, it's not just objects in secure JavaScript or some other language. It's electronic rights and escrows and auctions and various market institutions you want to be able to compose and combine to build your business application. And so I'm going to start there on down with where are we at. So we have been building up this system. There are many layers to it. We now are doing our first testnet, or we're close to doing our first testnet. It is in September of last year, we built the secure infrastructure for execution, not on a testnet, but when you've got application facilities, it's have a development environment that we could use. So we deployed that. It was called Playground. But the security kernel of that is the security kernel we need for fine-grained compartments. And that same security kernel was deployed, for example, as the security kernel for the Lightning platform at Salesforce. So all of Salesforce's App Exchange with their 5 million developers and 140,000 customers, or business customers, all of that is secured by the same security kernel that we built in conjunction with them for the purposes of using for partitioning of smart contracts and adding security for smart contracts. We are now working on the chain integration testnet. So this is the very first testnet where we're starting to all operate on top of a chain. We're going to talk about how we did that. It's built on Cosmos, integrating with Tendermint, integrating with Cosmos SDK, and that's what we're working on now. We're now deep diving into IBC, so there will be a implementation of IBC in our chain, interoperating with other chains that do IBC, and we'll be working with, as I said, ICF and AIB on the defining and implementation of that. And then at the end of this year, there will be rounds of testnet on the way, but the most interesting one is when we do a testnet of our higher level constructs for doing smart contracts. And we have some of those examples now in our current testnet to be able to start building up and developing that, which we have been doing, but there's a lot of rich additional work that we'll be doing in the future. And then finally, next year we'll go to we will go to mainnet with limited all the way out to full functionality. Okay. So I'm going to start at the top. We want to build a testnet. It's a very small testnet. So you may have seen the $1 million homepage or the R place where there was an Ethereum market where you would buy and sell pixels and so forth. So we're doing something like that, but of course, this is an early access testnet, so it's really just our 2 cents on this particular problem. So very small bits, but what's different is those pixels are a digital asset that is expressed with a small program in JavaScript. And we take that, and now we can take that and have two separate electronic rights that can be separately transferred. One is the authority to color the asset. The other is the authority to transfer the right to color it to someone else. And then we can build up from there with richer and richer abstractions. We'll talk about some of those as we go through. So on top of that, we can do derivative assets like a covered call, where it's not a covered call of a stock, it's the right to purchase that particular pixel from the owner of the pixel at some point in the future. Or we'll be able to do compound assets, which are a group of pixels that might make up a rectangle or a logo or some other abstraction that you want to be able to sell to people and build secondary abstractions like alpha blends or renting a pixel or time-bounded access to pixels or so forth. So this is a playground for starting to build the composable pieces. All of the abstractions, or many of the abstractions that we and others will build in this environment are obviously reusable for other use cases. The same covered call code that you could use to cover the selling of a pixel could be used to cover the selling of any other digital asset in our overall architecture. And so this is the stuff that we're building now, and there'll be things that we will add on the extensible piece. But let me be clear: there's no UI yet. There's a lot of these pieces that we're building over time. Our focus is the integration downward that I'm about to get to. So I could go through this, but this is actually we can talk about this later in the session at 4:15 where we deep dive. Once the testnet's available, this is the kind of process where here's an empty environment where you've got a pixel faucet and no money. The only thing you can do in this toy environment is get some pixels for free and then go to one of the market makers or go to the order book or go to some of the other participants in the market and sell that in order to get some of the money, which I believe we're calling dust. So of course it's pixel dust, right? Okay. So the initial environment is, obviously a blank canvas, and that's one of the things in a testnet is you can build all sorts of things. And we will interact with it in a command line interface. Now, the important thing about that is that's just a JavaScript command line. You can run any JavaScript you want there, and it will run in instances that are deployed to talk to the chain. The same environment will let us run such expressions on the chain, and because we can compartmentalize JavaScript in our secure subset, it's safe. We're not worried about it. Run anything you want. Now, so all of the modifications in our current UI are commands that you're just invoking in the JavaScript command line. And so, there's a sequence of things. This is very low-level expression right now. Obviously, over time, we will be building UIs on this. We will be providing other abstractions. Here, I go to the tap and ask the gallery, which is what we call this thing here, to give me a random pixel, and then later on color that pixel some random web color, which is, I think, the purple over here. And so then there's a bunch of interaction to be able to do this. But one of the things I could do is turn around, get the cell right, and send someone a payment in terms of pixels, which then they can say and claim the pixel exclusively, so that now they're able to color. Okay, so that implementation then is browser at one end. Remember I said we've got the ability to talk chain to chain or individual machine to chain or individual machine to individual machine. So browser at one end, which is that cheesy little UI you saw, talking to a solo machine running our infrastructure, where there's a web device, a web service that can do arbitrary web pages, arbitrary web service, HTTP, and it talks through our JavaScript programs, we'll go into a little bit more, and then to a Cosmos sending device that knows how to turn around and issue transactions on behalf of this user, where this is the user's software agent, into the Cosmos ecosystem. It does so submitting to the Agoric chain that is again implemented on Tendermint, and that does the work of the actual chain. It has the contracts, it has the marketplace, it has the actual pixel resource that is the issuer of pixel digital assets and so forth. And so I will now let him dive into more of how that all works and how we build how we build this.
So Dean described some of the motivations of the top-level economic machinery layer and the sorts of tools that you can build up there, the options, the auctions, the different contracts you can have there. And then below that, we have these other layers supporting that, providing the object capability framework that allows you to write those programs that manipulate electronic rights, and then the way that that framework runs on top of any given machine. So I'm going to start kind of from that object capability layer, talk a little bit about what object capabilities are, how they get wired together, and then how we have built a platform into allowing you to run that inside a chain, inside a Tendermint chain, or on a solo machine. So starting from the basics, objects are things just like standard object-oriented programming. They're things that have private state and they have publicly invocable behavior. And the important part is that they can protect their private state. Nobody from the outside can cause you to change your internal state without asking you politely. So in this case, we have what we call a purse, which is kind of one of our basic economic object types that has a balance, it has some kind of denomination, and of the things you can do to it, one of the basic one is ask it, what is your balance? How many tokens, how many dollars do you have? Objects are capabilities because in our field, in our lingo, capability is, in fact, a transferable, unforgeable authorization to use some object that it designates. So it both points to an object and gives you the permission, the authority to tell that object what to do. The nice thing about that model is that you can tell exactly what power a given object has by looking to see what references it has. It is a one-to-one correspondence between outbound references and authority. But in programming languages, that's just an object reference. It is a pointer from one object to another stored as an internal state variable that lets you send messages along it. The two kinds of messages that you can send, two kinds of invocation you can have. You can do synchronous invocation where the caller waits until the callee is finished and gets back a value in an immediate send, or there's eventual send. And eventual send says, I will schedule that call to happen on some future turn of my event loop, and I get back a promise for the result. This is really important because it's what lets you, it protects you against plan interference, plan coordination hazards. And for instance, the DAO bug from last 2 years ago almost now, was a classic example of what happens when the function that you're calling is allowed to do too much stuff before you get control back again.
Well, in particular, it's allowed to call back into you synchronously.
Yeah.
So you're in the midst of breaking your invariance, and then it calls back and shoots.
So reentrancy hazards are completely removed by making sure that you do an eventual send out to somebody. And in our syntax, in our subset of JavaScript called SES, Secure ECMAScript, the syntax for doing eventual send is this exclamation point. Instead of saying purse dot get balance, that's an immediate call, you say purse bang get balance, and it gives you back a promise for the result. And that syntax, that's sugar for calling a wrapper function around the purse object. So in a lot of our examples, you'll see this e.purse, but eventually we'll have a front end here that's going to rewrite some of these things, so you can use this syntax, which is a lot more concise. Okay, so now that we have these objects and they have references to each other, we put them into VATs. Each VAT is a unit of synchronous access. So two objects that are in the same VAT have the ability to do a synchronous blocking call to one another. Or if you have a reference to something inside your same VAT, you can do a blocking call to it. You can also do an asynchronous call if you want. Sometimes that's a good idea, sometimes that's important. But the important thing is that between two different VATs, you can only make asynchronous calls. You cannot do synchronous calls between two separate VATs. So we sometimes separate objects out into these partitions because we want to not accidentally make a blocking call to this other side. VATs are also generally the unit of progress. So any one of these objects could go into an infinite loop and prevent all progress remaining within that VAT. So you may want to put the code that you're evaluating that you aren't sure whether they're going to go into an infinite loop or not, put them into a separate VAT.
Can I just inject? So contract deployments where these are independent contracts representing independent interests would be in separate VATs, and they're just asynchronously calling each other.
Right. So then we go further, and we take a bunch of VATs and we put them into a machine. And we're still playing around with terminology here. You might call this a pod, you might call it a pseudo-kernel environment, but it's a lot like I have one server and I have a different server, and those servers are separated by a network. And so the machines here are the unit of determinism. The messages that arrive at a machine may arrive in all sorts of different orders, but somewhere inside that machine it's going to commit to a particular sequencing of the inbound messages. And once it's committed to that sequence, everything beyond that point is deterministic. So this is the thing where you want to, this is what you can turn into a chain. This is what you can do deterministic replicated computation on. So we have different kinds of machines. There's the machine that lives inside a chain, and it's basically like a Cosmos SDK module that processes inbound messages and changes its state and emits new messages. And then we have solo machines. And for a lot of these situations, I have some bit of code that I want to run on my phone, the thing that represents my wallet, the thing that represents my private interests. I may have a server that is controlling some other inventory, is interacting with some external system. Those are VATs, they're machines, but they're not chains. There's no particular benefit to having, and in fact there are negatives because chains can't keep secrets. Sometimes I want code to run in a private space, sometimes I need it to run in a highly replicated, highly credible space that other people can believe in. So we use the same infrastructure, the same messaging, the same programming patterns for all of those different environments. So the SwingSet architecture is like, it's sort of like a nanokernel for VATs. There's the different VATs are a lot like user space processes in a Linux box. And they all share this same kernel that they all talk to. Just like a user space process on your Unix machine does a system call down into the kernel. Every once in a while the kernel can dispatch a message back up into that user space process. We split these things up inside the SwingSet machine and cause all of the inter-VAT references to go through the kernel. So in VAT1 and VAT2, there's an object in VAT1 that thinks it has a reference to an object in VAT2. What it really has is a pointer into something in the kernel. And every time it wants to send a message, it really has to send that into the kernel. The kernel will think about it, decide where it wants to go, and then eventually the kernel does a dispatch back out into some user space VAT and delivers the message. So it's a kernel, but it's all written in JavaScript. So in some sense, it's a nanokernel because it's doing less than what a full kernel would do, but it is very kernel-like in a lot of ways. The two most important things that the kernel has to manage are the run queue and the capability lists. So as a VAT tells the kernel, I'd like to send a message to that thing that I imported from you before. The VAT has a reference to an object in some other VAT. What it really has is a pointer into the kernel and an import index. And so the VAT says, I would like to send a message to whatever it is I'm importing at this index. And the kernel has to say, oh, right, what I told you was import index number 4. Really, that's coming from that ABC over there, and it's that thing they exported as index number 5. So this translation table goes through a thing called the C list, the capability list. That is both there to help get the message to the right place, but to also limit what that sending VAT gets access to. So there's no way for that VAT to send a message to anything that is not on that list. And that's kind of a key security property because you want to make sure that the VAT can't get access to anything that has not been previously granted. Once that translation takes place, then we append this to the run queue. This is what causes it to be run in a future turn of the event that protects us from the planned interference and the reentrancy hazards. And then eventually this pops up to the top of the run queue and we have to dispatch it out to the target VAT. This goes through another translation step where because some of the arguments inside this message might point back to the original VAT. So as the kernel translates this message to be delivered up into the receiving VAT, it has to take all the argument pointers and rewrite those references to say, guess what? I'm giving you, you're thinking of this as import number 12. You don't know where it's coming from. You don't know which VAT it is. The only thing that that receiving VAT will ever do with that import number 12 is tell the kernel, I want to send something to import number 12, or I want to reference import number 12 in the argument of some other message. And so the kernel is updating that C list as it sends things into the target VAT, or it's referencing that table as it goes through.
So, and what this is doing is, this is the kernel now enforcing the, I've got an object handle, I can pass it around semantics. This is some of the mechanics by which an OS kernel achieves the object, the sense of simple object pointers and preserves simple object programming for the things built on top of this.
Yeah, the C list table is very, very much like the file descriptor table inside a Linux kernel. You know, the process has, yeah.
So basically, this is more like a restriction engine, right?
Yeah, yeah. Although it's an access engine, and there's nothing else. The only way to get access to anything is to go through this table.
So it's a dynamic.
Yeah, basically, if I hand you a pointer conceptually, I hand you a pointer conceptually, that is registered in the CList table as saying you have access to that and only. And Chris would not end up with access to it. He would only have it if I handed it to him. And so it's not that it's a restriction engine, it's that it's an engine that is representing the access graph your program created. So it's not something that someone comes along later and says, oh, I'm going to pull this, I'm going to add that. No, the programs are just handing around pointers. This is how that's enforced. And then the thing is, the kernel can now make that persistent because it can remember, okay, when I restart, you know, that VAT has access to object 37 in that VAT because he gave it to him.
So it's basically like a dependency graph, something that, for instance, a garbage collector language already
It's
has.
just like that.
Yeah.
Okay.
I think of this as the object table in an object language.
Yeah. And it's very much like the file descriptor table in a Unix process. You know, when you do a syscall in Unix and you say write to file descriptor number 4 with this number of bytes, that 4 is looking up a table. Inside the kernel, it knows what actual file object that points to, and maybe multiple processes all have pointers to the same file object. But from the process's point of view, it's just an integer. And so the syscall boundary we have is just saying import number and gives it an integer pointer. Okay, so given that model, all of these VATs are limited to talking to other VATs. In fact, all of these VATs are limited to talking to the kernel. How do you then have this have any influence over the outside world? In our system, we've defined the notion of a device, very much like a device driver in a Unix world, where this has some sort of out-of-band, out-of-VAT, outside of the kernel itself, access to maybe a piece of storage, to maybe a clock, to some device, you know, turn on the light switch, that kind of thing. And we have them communicate with our VATs in the same fashion. There's a CList that points to some device node that's being published by this device. And the main thing we're using this for right now is communication from this machine off to some other machine. So you make a device here called the Mailbox device. We allow VATs, certain specially privileged VATs, to write messages into the mailbox that can then be read externally. So all messages going from one machine to another have to go through this mailbox. The only way to get from one machine to another is to go through a network. The only way to get to the network is for something to notice that the outbox has been modified, write it out to the network. On the receiving side, somebody receives from the network, they write it into an inbox device, and eventually that gets delivered into the kernel and triggers a message delivery to some other target object. Now, when these machines, because these machines are now entirely deterministic, it's entirely a function of the previous state and then the inbound messages, whatever order they arrive in, we can replicate this. So the whole state of the kernel, the whole state of all of the VATs, all the state of the devices are all just data. And it's a deterministic function of the input, so we can replicate that, we can hash that. All of that is going to go into the Cosmos SDK keepers, into the storage devices that are there. And then that's all included in the state tree that is hashed up and represents the app hash at the top that Tendermint then validates on. So in our testnet, in our current mechanism here, the outbound messages are being written into this outbox. And the receiver of that, the follower that wants to discover that the chain has sent them a message, is going to do ABCI queries to go in and say, hey, tell me about the contents of your outbox. And if I see something in there that's for me, great, I'm going to go parse that, I'm going to treat that as an inbound message, I'm going to deliver that to my machine. So that's how messages get from a chain to a solo machine. For the other direction, that's, no.
Sorry.
That or not quite. For sending messages from a solo machine into a chain, anything going into a chain has to be a transaction of some sort. There has to be somebody that signs a transaction, sends it in, it gets delivered off to a handler, so some module inside the Cosmos SDK. So for us, the solo machines are capable of talking to the network, right? Chains are special. Chains don't have any secrets. They're replicated. They're highly credible. They're highly reliable. But they can't make outbound network connections because everything they do has to be deterministic and replicated and validated across all the different validator nodes, which means it's as if I want to tell you something, but I have no voice. All I have is a book, is a journal, and I can write notes down in my journal, and I'll just kind of leave it on the table and hope that somebody comes along and notices it and acts upon it. Whereas a solo machine, it has a voice. It can make an outbound network connection, it can keep secrets, it can sign messages because it has that private key. So the solo machine is going to sign transactions with a message destined for the SwingSet machine inside the target chain. And then it's going to broadcast those as anything else would. It'll do a broadcast TXN to the RPC port on one of the validator nodes or something that will replicate it. So that gives us kind of 4 types of message delivery. So when a solo machine wants to talk to the chain, it's going to create a transaction, sign it, broadcast it in, that gets delivered. When a chain wants to talk to another chain, that's basically IBC. That's where the chain is going to write something down in its journal, either in a state vector or as the result logs of transactions are being processed, and that's all it does. And then later, some relayer comes along and notices that. It's following to look for those logs or for that state vector, and it notices there's something in there that needs to be sent to some other chain. So the relayer is then going to sign a transaction with its private key and broadcast that into the target chain. And this is basically what IBC is. We've been working on this since before we started work with the ICF on IBC. So our prototype is not exactly using IBC, but it is very similar in spirit. And we will be aligning this process with the actual IBC as we're working together over the next several months. When the chain wants to send something to a solo node, because it has no voice, all it can do is write something down in the journal. And so the solo node is actively querying that. The solo node is able to be an RPC client of the Tendermint protocol and follow along and discover when a message has been written to the state, to the outbox piece of the state, and that's something the solo node needs to act upon. And then when a solo node wants to talk to another solo node, well, that's just regular TCP. That's just a direct network connection from one place to another. This is the layer that can actually have transport level security. These are the things that can keep secrets. And so a lot of the work in our community, a lot of the VATs that we've been building until blockchains came along, were entirely this bottom bit. It was entirely, make a TLS connection to somebody and then send some messages back and forth. So as Dean pointed out, our kind of initial testnet client is just going to be a read eval print loop that's talking to this. So we have a solo client. So the testnet zone that we're running up on a bunch of different cloud servers. Every participant in the testnet is going to run the client machine on their own local machine. And that's going to be it has the ability to talk to the chain, but it's also a solo device, so it has the ability to make network connections and set network connections. So it's listening on port 80 locally and serving up the basic demo page that has the REPL, and has the place to type in the code, and has the $128 homepage small pixel grid. And every time you do something on the front-end browser, that sends commands in over HTTP that tells a VAT inside the solo machine to either do something locally or send a message, sign a transaction, send a message, and send it up to the chain. And one of the things it will do when it starts up is to subscribe to find out about changes to that pixel grid. And then the chain will send messages down every time you or somebody else changes the color in the form of writing a message to the outbox. This is subscribing, this notices that message to the outbox and says, oh, hey, that's for me. I will deliver that message to the demo client object, which then sends a WebSocket message down to the browser to say, hey, change that pixel at 4.5 to red.
And all of those elements, are all the basic elements you need for almost any DApp, right? That this is an example to do an end-to-end of the least possible thing, but it's the least possible thing that achieves the replicated execution on a persistent chain agreed with Tendermint, et cetera. Now, at the actual digital rights that we talk about are being traded, exchanged, and so forth with ERTP, the Electronic Rights Transfer Protocol, which is at that contract layer that I mentioned, and some of the work it has been there. Out of this infrastructure and with ERTP in the current test environment, we can build derivative digital assets on that where, as I said, covered call, timeshares, rented, and so forth. And so one of the things we will be doing as we open it up to people to participate is starting to work with people to actually build some of those so they can, so we can get all the way from those compound assets like rectangles with pixels into interaction on pixel groups, so you can start to have games or life or processes that are trying to acquire options on enough pixels to get together a rectangle to be able to rent out rectangle space for ads or whatever it is. And so this is just starting the build towards composable contract components, but this gives us the platform to start working with initial partners where we can start to build the contracts that they need for real applications once the system rolls out to mainnet, and we can have people start to experiment with new kinds of financial instruments that are just expressed in the JavaScript that they already know and are already familiar with and have already built lots and lots of apps in. So that's what we're building. And at 4:15, several of us will be upstairs to talk.
Why did you choose to create a separate you call Soul node? Why did you implement the entire client in actually JavaScript that run in the browser?
This thing here, you mean?
Yeah.
Yeah.
I mean, you're introducing a second layer of complexity.
Sure. It would be nice to do everything in just JavaScript. There's so much of the Tendermint. So our initial implementation of this used a separate Tendermint client and a Nodejs process, and they speak ABCI to each other. So we get all of the consensus mechanism from Tendermint, but everything else we're responsible for. And for instance, Lotion takes that approach, right? You write something in JavaScript, and you're implementing all the different message handlers. But we regretted the fact that we then couldn't take advantage of everything that's in the Cosmos SDK, all the existing modules for banking, for authentication, for staking, all of that stuff. And in addition to that, looking at the way IBC was going, IBC is going to be a Cosmos SDK module, and really want to interact with IBC. So we don't want to have to write all that stuff as well. So just a few weeks ago, and the other triggering factor was we just hired a couple of new people, and one of them has enough information, has enough knowledge of both Go and Node.js to help us write some of the glue to go and connect these two things together. So in fact, we'll talk about this more in a breakout session, but what we have here is a Node.js process that embeds the Cosmos SDK as a library. And it does foreign function interface calls between those two language boundaries to start the SDK and have it listen for inbound messages and do the peer-to-peer protocol. And then the SwingSet mechanism is just one module of all the different modules in the SDK. Every time a message gets delivered to it, it gets thrown over the language boundary off to the JavaScript side, back over to Node, and we do all of that processing. And what we found was, the complexity of this is annoying, but it's necessary for us to both be able to use the JavaScript environment that we want to be able to provide these contracts in SES, in the secure ECMAScript subset, and take advantage of all of the libraries and all of the rich work that's already gone into the Cosmos SDK. And what we're looking at for the future, we're basing this on Node.js right now. Node.js is kind of large. It's kind of too much, and we're not comfortable with the security consequences of having something quite so large. So there is a different JavaScript engine called XS, written by a company called Nodejs, and it's very much aimed at embedded devices. They sell thermostats or washing machines that you can program in JavaScript to get the stuff built. So it has a very, very small RAM footprint.
And Whirlpool washing machines, Maytag.
Yeah.
not Podunk.
But so you can write useful JavaScript programs that then take a few kilobytes of RAM and put it onto a 5-cent microcontroller with their engine. So what we're looking to do is take their engine, which is written in C, and compile that down into something, maybe into WASM, and run that embedded inside another one of these environments. So we really like JavaScript for writing the contracts. That's the language that is particularly well suited to doing object capability work. But we don't have to have the whole system. The kernel doesn't really have to be in JavaScript. That was just the most convenient thing to start with. So we can wind up with each of the individual VATs is running JavaScript, but the engine that's supporting that is in a different language and is embedded inside a different program. So we could put that into Go, we could put that into Rust, we could have other environments here. And in the longer run, we're looking to run on lots of different chains, lots of different kinds of chains. If we want to embed this into Ethereum, if we want to embed this into Polkadot, then it's going to be the same runtime, the same JavaScript engine, the same API to it. But the host that's providing that and the way the consensus is done is very different on each of those platforms.
So I'll also add one more thing. So we opted to prioritize getting the full Cosmos integration, so we do the Cosmos SDK. What you described is where we started, and we will do that. I mean, there's no question that being able to have the browser directly connect into the chain is of value, so we don't have to have that extra server.
Yeah.
From the point of view of proving that any of these work, that wasn't high priority. We'll get back there. So right now we're taking advantage of the integration with Cosmos SDK. We're taking advantage of a few things that are just Node IO stuff. But there's nothing about that we don't expect to be able to run in the browser.
Right. So of the different machines, one of those could be a chain. One of those could be something long running that lives on a server somewhere, and it's a solo node. One of them could be in the browser. and it can speak those protocols directly. But to get there, we're going to have to take a lot of the Tendermint mechanism and write that in JavaScript. We're going to have to take a lot of those messaging protocols and rewrite those in JavaScript.
And we've been working with the Lotion folk that have some of that, and we'll be working on a JavaScript-only IBC implementation, in which case we can plug that in, and then we no longer need the.
So, do you also have something like an abstraction layer? I mean, if you told me that you want, for instance, in future maybe to integrate Ethereum or Polkadot or whatever, do you have an abstraction layer, or right now everything is focusing on, on Cosmos?
So we have multiple abstraction layers.
Yeah. I mean, we've got the big picture.
Well, no, I wanted the specific technical thing.
Okay, but so in the big picture, there could be a public chain of one type, a public chain of another type, an Ethereum one, Cosmos one, Polkadot one. But in all of those, there are vats, and in all of the vats, there are objects. And the code in the object can't tell what kind of chain is running it. It uses a uniform messaging mechanism, uniform runtime language for all of those.
So you can have a contract running on a Polkadot subset of this chain, sending messages, same messages to a contract running on the Cosmos.
Yes, but this still has specific stuff for each type of chain.
So this interface here, so I said there are multiple levels of abstraction. So most of the runtime is identical. Right. This interface here, this syscall interface is like a kernel mode, user mode, kernel mode separation, or user mode, system mode separation, and that will be well specified such that this can be implemented in Rust and compiled WASM. Then there's the engine to enable you to run JavaScript up here, but that boundary could be a WASM boundary or it could be native. Right now it's native, and so those are so. We know what those architectures look like. We've done, we're part of the WASM committee, for example, and have done work to make sure that we're able to target those environments. So yes, we absolutely will be able to have that work. The key thing about this VAT architecture is because the kernel is the one that is arbitrating the handoff of pointers, it's achieving the simple object-oriented style of usage by clients, but in the same way that it's able to be the place where we say, okay, everything below here is persistently managed by the kernel, it's also the place where we can go, okay, if you want to migrate this VAT to another runtime, I know just the plumbing I need to do, so you can go over there and I will forward all messages that come into this kernel for this VAT, they will now be forwarded over to that other chain. So that boundary is the boundary of containment and migration and everything else.
Imagine the smart contractor interacting with the host of some economic interaction that's living on that particular chain, and you decide, you know what, I don't really like where that chain is going. I think that other chain looks more popular and looks like it would be better supported. Move the entire VAT over to that machine, update all the references to point to it, and great, now the VAT can outlive the chain. Another point here is, like the system call boundary allows user space processes to have this very narrow, very well-defined interface to the kernel, that enables the code in user space to be written in whatever language you want. So we can have something here that is using our JavaScript style thing with the bang syntax and those object references. You can write it in a different language, as long as it still kind of has this notion of references that it can invoke. Then you can use lots of different approaches. And another thing we're using for that, our current mechanism uses a thing called orthogonal persistence, where when you write your code, you don't need to think very carefully about where your data is getting stored. It'll just be there again when you come back to it. That is useful for some things. It's more troublesome for some other things, like upgrading to a new version of the code. So a different implementation of this layer could choose a different state management approach, and it still uses the same kernel interface. So you just kind of swap this out for a different module and you get that other behavior.
Now I will be very, since for the audience out there, we can do those. They are, our focus right now is getting out to mainnet with our current model, and so they're on our roadmap and radar, but for later.
Any other questions? All right.
Thank you all very much.
Next question, come on by at 4:15 for a breakout session.